Thank you, Debbie, and good morning, everyone. This is a project that we're doing under CCAT, and an objective is to aid older drivers in gap selection situations at the unsignalized intersections. And from the outline, I'm going to emphasize on the older drivers and also on the data collection and application of parameters. And as we all know, the nation's population is aging. And one example shows in the underlined on the second item here, from 1997 to 2018, it's approximately 20 years. Older driver age of 70 and older increased to 65%. And that lead to, you can see the third item here, a lot of fatal crashes. 6,700 people, older drivers, die. And roughly every year, this is from my memory, for many years, this number is in a very close range. Approximately 50% occur in intersection related or at intersection. And especially the last item shows stop sign control intersection. Nearly 2,000 fatalities every year. So it's a main issue here. And here shows older drivers overly represented. And the horizontal axis shows the age, and the vertical axis is the percentage in fatal crashes. So you can see as people turn 65 or more, you can see the curve goes up so quickly. And the chart on the right shows that the fatalities for people 70 and older stay pretty much in the range for many years. You can see that, okay, between 4,000 and 5,500 range. So it's a serious problem that we will have to deal with. Now here's another chart to show the statistics. For fatal plus injury, you can see the crashes intersection related is 56%. But if you look at the right, among those fatalities at intersections, unsignalized intersection, you can see that take a huge, a majority. And why is the problem? Why unsignalized intersections seems more dangerous, more risky? That's because driving is not easy. Okay, as David just mentioned, this presentation probably is not just for older drivers, although it's harder for older drivers to conduct a study for older drivers because of, it's hard to get enough samples, and not enough people work in this area has been done. But anyway, driving requires, ability in those 6 domains, from a mental status, you go down to these, and to execute executive functions, to memory. And the most important is the mental status, because that deals with the general cognition. And execution functions are, relating directly with the time, of course, is critical. And the last, memory is not the least, because you can't imagine a driver with like serious Alzheimer's disease pull up to an intersection and waiting, and then they forgot about the car coming, from on the main line 2 to 3 seconds later. That can be very dangerous. So we all wish we can be forever young, and not just a wish. Problem is, when people get older, we lose our abilities, as listed here, you can see. From functional limitations to even physical vulnerability. Can't compare with young people. Now, cognitive functions are so important for driving because it concerns with the concentration, the execution, and and of course your memory. And specifically related to this research, at the places where auto drivers need to select a gap to enter the roads, enter the intersection. From a gap selection to making a turn and emerging and also speed up, and the whole process should be smoothly executed one after another. Any element, problem in any element can lead to safety, risk, safety concern, and even, accident potential. So the problem is at unsynchronized intersections, as shown here, we have a T intersection to represent the, a sales two-way stop. But the T intersections and stop sign work the same way. That is, vehicles on the main line have the right of way, and the vehicles coming up from the minor road will have to make a full stop before finding an acceptable gap to enter, either making a right turn or left turn, or choose to reject the gap and waiting for another one. Now, drivers reject the gaps, many reasons, okay? Simply it could be just there's not enough time, if the judgment is correct. Or this is a result of a misjudgment because of the poor sight distance or high approaching speed, or simply just the indecision because of the lack of attention. Many reasons for that. Now, a critical gap concept was introduced many years ago, and it refers generally to the minimum time for a driver to enter the intersection. Okay, it cannot be smaller than that. It's a minimum time. And there have been several ways to define critical gap, but in this research, we use the one that defines it as the point where the number of gaps accepted and the number of gaps rejected are equal. Now, it should be noted that critical gap is affected by location and environmental conditions. Therefore, it is intersection dependent. It varies, between intersections, among intersections. Now, studying gap acceptance behavior by auto drivers started many, many years ago. And you can see that, on rural roads and comparison day and nights, and auto drivers hesitation and until rejecting longer gap, accepting shorter gap. So number of studies, this is just a small list to show that we have started to work on this many years ago. So guidelines are developed. And for example, here, we should not use a PRT, which is the perception reaction time, less than 2.5 seconds for auto drivers. In addition, the Federal Highway Administration recommended that for left turns for auto drivers, we should use really a gap of 8 seconds, not less than that. On the average, if you open the highway capacity manual or AASHTO's Green Book, an average time of 6.5 seconds are listed, okay, for, it's a little slightly difference between left turn and right turn, but on the average, it's 6.5 seconds. Now, with today's technology advancement, how can we help? Number of things listed here, and we know the newer models of vehicles already have built in some of the functions, like this here, blind spot and fatigue and lane departure, adaptive cruise control. And as the list goes on, and in the later part, you can see that it requires more automation functions from vehicles. Now, I highlighted one, that is the collision warning at unsignalized intersections. That is also one way we can help the auto drivers. And that is a focus of our project. Now, connected vehicle technologies, we understand they can help in different areas that we're all familiar, by today. Now, people also realize that you can see that in more recent years, a lot of work have been done, starting, ranging from surveying the auto drivers for their acceptance of the idea of connected vehicles to a simulation-based automated speed control to unsignalized intersection to avoid conflicts. And you can see also in-vehicle intersection crossing in the human factor lab, to some lab, experiments to studying the cooperation of connected vehicles at unsignalized intersections to help the auto drivers. So this is a simple list again. And then more or less, those are all simulation-based and in a lab environment. And also, most of them consider just a pure either connected vehicles or autonomous vehicles. But more realistically, in a near future, I would say probably a long near future, I guess, we will have to deal with a mixed traffic where we have connected and automated vehicles, as well as regular vehicles. We call it ordinary or regular or conventional vehicles. And then a study to involve auto drivers in the fields, really it can contribute further to this whole effort. And that's our study based. So the objective of our project is to develop an auto driver safety advisory system by providing information for auto driver to avoid unsafe gaps. And the system will make use of the V2I data communication technology. And as I mentioned before, importantly, we are dealing with mixed traffic. So what we'll do here is not only to develop the control logic and algorithm and software and the hardware, we will run a simulation also, because it's really very difficult to collect the data involving auto drivers. But then if you notice, I have underlined here, our simulation is not just purely simulation. Okay, it's a simulation based on data extracted from field involving auto drivers. So that is more specific, it's targeted. And of course, we will do also a field test with auto drivers about our system. We select a couple of intersections, and the objective of field test, of course, is to see the feasibility of the proposed system. And also we want to find out how the auto drivers accept our system, especially how the information is delivered. So let me discuss the system. We select the T intersections to do the experiment and research, simply because it's, for finding location where the senior citizens live. And in most places we have a T intersection. And plus also there's some age requirement too. We'll discuss that later. We have considered two situations. So one is controlled situation, and that is all the vehicles are able to do V2I communication, specifically to the central terminal. In the uncontrolled situation, where only the auto driver vehicle has that capability, because we assume our system is installed in the auto driver vehicle. But the other vehicles on the main line are not able to do this V2I. So this is, a purely a mixed traffic situations. In a controlled situation, and this is how it works, the whole system, when the auto driver's vehicle pull up to the minor roads, stop sign there, before it gets close to that place, it requires information from the central system, central terminal. And then the central terminal receives 10 times per second the location and the speed information from the approaching vehicles, from those mobile sensors inside the approaching vehicles. And then the central terminal will process the information to see if the approaching vehicle's gap is safe or not. In case it's unsafe, then the central system will send a request to the system module in the auto driver vehicle to display a warning message, either by sound or flashing light or both. The system components will include LCD, GPS module and Zigbee for data communication, and of course a microcontroller that runs the whole system. And here is a simple sketch to show when the auto driver vehicle pull up to the stop line here, and this is the central terminal, closely located at the intersection, communicates with the auto driver vehicles to share information about the oncoming vehicle, the approaching vehicles. And especially, it's just that, if it's unsafe, then they will ask the display inside the vehicle, auto driver, to show a warning. It's a simple concept. I don't think we have time to go through this, but this is the simple system workflow. But in the uncontrolled situation, it works pretty much the same way, except in the middle point there, okay? The information, the location and the speed information is not sent from the mobile sensor inside the approaching vehicles, rather is from roadside sensors. So for that, we have to have additional hardware, as listed here on the last part of this page. We have to have traffic sensors, okay? And of course, with the Zigbee and and microcontroller to collect the information and send the information to the central terminal. And this is a simple sketch to show that. So this is a traffic sensor, okay? And that communicates with the transmitter here, and from transmitter to the central terminal. That's how the information, the data relate. And this is the workflow. Let's go through. And the gap estimation is pretty straightforward. It's just simply distance divided by time, divided by the speed. And now the safest condition, we want to make sure that the gap that we consider as a good gap to use should be greater than the critical gap, and of course greater than the stopping sight distance. In most cases, this criteria is met because the stopping sight distance really is the smallest distance, okay, for the vehicle to stop, to do emergency stop quickly. And vehicle turning from the minor roads, of course, they either turn right, turn left. But for left turns, we all know it's more complex. It requires a safe gap from not only the eastbound traffic, but also the westbound traffic. And this is the control logic for that. And pretty much I explained. And here I show this chart again. And this is the condition, and that is for single lane situations. Now, many cases we do not just have a single lane, we have like a multi-lanes. Now, in case of multi-lane, we have to check on every lane. The case, you can see there are two equations that have to be satisfied. And for the left turns, this is a control logic. And it's a little more complex, simply because we have vehicles coming from the left and from right. We call it eastbound and westbound. And you can see the condition have to be satisfied. Both conditions have to be satisfied at the same time in order for the driver to have a safe gap. Now, in multi-lane situations, then we have more conditions. You can see. I have a simple video to show the idea that we presented here.
Don't turn. Don't turn.
So let's move to the simulation. I mentioned that we still need to do simulation because of we cannot just because our limitation to collect the data dealing with auto drivers. Now, of course, the simulation I mentioned has its purpose. Listed two here. One is to study the impeded speed. Now, what do we mean by impeded speed? A lot of studies have found that auto driver vehicles create blocking effects to the approaching vehicles after they merge into the mainline flow. This is a safety concern, especially when the auto drivers select a very short gap. And the next point is we want to study the impact on the traffic operation. If we use either 6.5 seconds in the highway capacity manual or the Federal Highways recommended 8 seconds critical gap as the gap that we advise auto drivers, if it's less than such gap, do not enter. We want to see if we do that, what kind of impact on traffic it can create. So that is the purpose of simulation. Now, I mentioned simulation parameters. 6.5 versus 8, that's the critical gap we use assuming after our warning system, safety warning system installed in the auto driver vehicles. Then we compare that with the field data-based gap acceptance distribution. And this is a concept that's very important I want to mention, because many studies do not consider this. What do we mean by field data-based gap acceptance distribution? Well, from the field, we collect the data how auto drivers select the gaps. I mean, it's understandable that not every auto driver will select a gap that is like 8 seconds or 6.5 seconds or 8 seconds or longer. Some will select the short gaps. But if we have that kind of data in the field, then we can develop this kind of curve or a distribution table, and our simulation based on that will be more specific, targeted to auto drivers. So this is something we must do in order to have the data and the comparison, more meaningful. So we had a couple of intersections and issue here. This is a T intersection as the red arrow showed. And here is the senior citizen compound here. And you can see it's very close to intersection. Many people come out of there. Now in Ohio, I guess every state may be different. We have certain places have age limitation. You have to be 65 before you're able to live there. So this is one of the such places. And this is a more close view of the intersection here. You can see, and that's auto driver coming out from the parking and enter this minor street from the minor road to the main road. And our equipment's, set on the side here, but we'll get to that later. Now, to prepare for data collection, and we used, some stuff in here. You can see on this on the right. But also we try to do the assign the interval distance so that we can count for the gaps. You can see different vehicles approaching, and if the driver starts to select the gap, we want to know how long the gap is. And that's difficult to do that in real time. So we found we use this way, we can collect some data first. How to do that? I mean, it's difficult, right? But we use a recorded video. Now the procedure is, whenever a minor street vehicle pulls up to the stop sign, we collect the data, and that'll include the age, direction, gender, and gap selected. As I mentioned, we use a video. We have videotaping for the roadside, and mainly to identify the driver and so on, more close. But the other one we use the drone to videotape so that we can compare. We can extract the gap information. We have a lot of drone video. Here is an example of the data at the intersection 1. And we did it several times, and roughly, the traffic volume is around 100 here for the minor roads, but for the major roads, we have like between 600 to like 1,000, and we have all the rest and the number of gaps are selected. So that gives us some base data to work on. Here shows another location because we can't just do on one location. There's another place also with age requirement there. And that is also a T intersection. And this is another video to show that. And some sample data we summarized and showing here. As you can see, we have number of older drivers and not older drivers, gender, whether they make a left turn or right turn. And the last part here, I show my mouse cursor, is the gaps they select and how many selected, a different size of gaps. For example, in study 1, we did several studies as shown here in the lower right-hand side here on the different dates. For the first one, 63 older drivers selected gaps that are greater than 8 seconds. And then we do have 8 seconds, 7 seconds, 6 seconds, 5 seconds, 4 seconds, even 3 seconds, you can see. We have people selected that for the different times. And then the lower part of this chart here shows, some summarized data here. So we will not have to get to those percentages. But I want to just sort of summarize the data. We found roughly 36% older drivers accepted the gap size less than 6 seconds. That is of concern because by having capacity manual or in the green book, 6.5 seconds are used even for general drivers. In particular, the 6% from our limited data, show that 3 or 4 seconds gap used to enter roads. And also we found 15% of older drivers rejected at least one usable gap of 8 seconds or larger or longer. What do I mean? What does it mean? A gap is usable, but they reject it. And of course, more than 35% cause a speed impedance if they select a shorter gap. That will force the approaching vehicle to slow down. And we have some other, observations, but then the last two points I want to mention. Left turns seem to reject gaps more than a right turn. And of course, if you use 8 seconds, if from the data, a longer gap is slightly more rejects the gaps than the 6.5. 8 seconds longer. Okay, more, let me rephrase this. Okay, more reject the gaps for 8 seconds gaps, okay, than a 6.5 second gap. We also did critical gap analysis. From intersection 1, we show that the critical gap is roughly at 7.4 seconds, but for intersection 2, it's 6.5 seconds. So when we try to do the simulation, we are, again, the objective is to compare. If we use an advisory gap size of 6.5 or 8, compare that with the field data-based distribution for the accepted gaps. That, remember, we have some at 8 seconds, 7 seconds, 6 seconds, 5 seconds, 4 seconds, 3 seconds even. But use the same kind of distribution. Let's compare if our safety warning system, if we implement that, would cause any impact on the traffic. That's the objective. Here shows some results. And this is a delay, intersection delay. You can see at 35 mile per hour speed, if we use 6.5 seconds as the critical gap, in other words, if a gap is less than that, we will warn drivers not to enter. And then compare with the field database. The field database, in other words, is like natural, is what happened today, nowadays, currently, because drivers select even shorter gaps. Results show that, okay, very close in terms of the delay for different volume levels on the main roads. But if you notice, read more carefully, the 6.5 seconds critical gap situation here is doing slightly better. You can see that, doing slightly better. Different colors show volumes on the minor roads. Okay, this is a simulation, we're able to do that. But reality, then it's hard to do at different scenarios. Now, in case of 45 mile per hour, you can see similar results. However, again, the 6.5 seconds critical gap situation, it shows the delay is a little smaller. Well, the chart doesn't. The chart has a little bit different scale because I want to fit that in one page, so I have to change the scale a little bit because this first line here is 200, but this line is 150. That's, by the way, the simulation in 1 hour. So you can see that. So the 45 mile per hour situation is a little better. And we did the 8 seconds gap time, the critical gap also. As you can see, the results are very similar too. And again, if you pay attention to read this, and the scale is a little bit different, again, in order to fit the whole page for comparison purposes. And the 8 seconds critical gap situation is doing a little better than the current field data condition. At a 45 mile per hour speed, similar results, okay? Again, the scale is a little bit different, so it shows, so, we could improve that later, maybe by using exactly the same and maybe make the chart a little smaller. And we also did impedance speed, of course. And you can see, comparing 6.5 seconds critical gap with 8 seconds critical gap, the impedance speed, it doesn't change much. This is when the minor roads volume is 200. And if you change the major road from 600 to 1200, you can see the difference is still not much on the impedance speed. Now, if we use a 400 vehicles per hour on a minor road, and then you have 600 on the main, and also here's 800, you can see the difference is still small. What does it mean? It means that it uses 6.5 seconds or 8 seconds, really it will not create much difference in terms of impact on traffic. So as a summary, we listed here implementation of the auto driver gap selection warning system. Not only potentially, if we do that, enhances traffic safety because we advise drivers do not enter smaller gaps, but also it may help improve traffic operations at unsignalized intersections because of the data shown there. And then what? Why is that? Well, we attribute to the improvement on traffic operation, the improvement on traffic operation to likely the fact that since older drivers enter the roads selecting larger gaps and avoid selecting shorter gaps, they create less interruptions and less blocking effect. That's why overall improve the intersection operation. That's our interpretation. But further study need to be made. Okay, that's why we said it may help. And of course, the difference between using 6.5 seconds critical gap or 8 seconds critical gap, really small. All right, so here comes to the field test part. I can see, there's a snow and winter time. It's tough, but this is the difference in a very simple way to explain, okay, between a controlled situation and an uncontrolled situation, where you can see the uncontrolled situation, there's no communication between the major road vehicles to the intersection infrastructure. That's the central terminal. And also we have other sensor link built into it. Well, in terms of equipment, we discussed that a little before, but it's showing here again. This is what we use to do the field test. And the sensors, the transmitter is placed at least, just it's far away, roughly 600 feet away from intersection, so that there is enough time, a gap for driver to use, right? And of course, the purpose doing the field test, we did a simulation, but what is the purpose of doing the field test? Main objective is to test if the concept works. The feasible is feasible that we can even use, a small effort. We can make this whole concept work for providing information for auto drivers. And the other one, of course, we want to find out from the auto driver. This is not in the human factor lab. This is a real situation in the vehicle, in their own vehicle. If they would accept the system, the safety advice of system, and also what kind of information delivering methods, like sound, lighting, or maybe both. So that is another objective. And here's just some stuff we show that we use, and this we now packaged it well in a box, but this is just to show what we use. You can see it's almost, everything's there. Where is the picture of a drone? Oops, let me see. I thought I put it here, but anyway, it's not here. But we also have a drone that we use that to record a video. And here it shows again the different parts. The different parts are placed in the different places. You can see central terminal and sensors and transmitter and so on. This is in the uncontrolled situation. And in a controlled situation, similarly, we set it up this way, and it takes time to do this experiment. We have divided our people into two groups. One is on the minor roads, and their objective is to collect information whenever there's a vehicle, on the minor roads, stop sign, about age, turning direction, gender, gap size, and so on. Now we do have situation in the post data processing that the driver, some drivers are not older driver, can tell because we videotape very closely. But of course, without letting them see, because it's a far away, but we use a very good camera to zoom in so that they will not be bothered. And that we understand it could be the staff working in the facilities or nurse or whatever, or even relatives visiting. But nice thing with this is during this pandemic periods and the visitation even was not allowed. The most maybe they can visit senior people outside, not going in. So maybe just by open a window outside, window to talk to the older driver, to the older people. So that helped us actually the identification of the age group. The other group of people in doing the research is at the major roads, and their objective is to count volume, identify the gaps. Now, in this case, we have the drone flying, okay, and we know the distance and the gap that in the post data processing. And of course, they have to control the drone to the videotaping. So I have a lot of stuff. Every time I go to fields, that takes. And this is the a flow chart for this work, but I don't think we need to discuss that. It's too tedious. Now I want to show this last page, just to show the difficulty we have experienced, in the last year and more than a year. We have not been able to actually conduct the work inside the older driver vehicles because of the pandemic, of course. But with today's vaccination and the speed, we hope the situation will change soon, that will give us the chance to actually test the system with older drivers in their own vehicles. So now we'll conclude my presentation, and I thank you for listening, and I will be happy to answer any questions.
First one is, did you find any variance in gap acceptance related to the vehicle type approaching? For example, smaller vehicles like a bicycle, motorcycle, or larger vehicles like heavy trucks?
Good question. We have not. We can go back to the data because we have the video. I mean, that's good to see there may be a difference, but intuitively, you could, because larger size vehicles but for speed, we noticed that, faster speed, and that will turn to have more rejected gaps, even the gaps is usable. But a good question. We can go back to check on that.
Okay. Do older drivers believe the warning due to their increased disability in field of view and looming? Do they overly rely on the warning and move without checking or ability to perceive?
That is a very good question, and we were concerned even before we started to do the project. That's why actually we don't. Our message, that does not tell the driver, to go. We just only driver when it's not safe to go. In other words, to stop. Do not want them to go if it's unsafe. But this is a similar situation that my previous project when I was in Minnesota DOT, and we designed a curve warning system. Some rural area roads and the curves are because of the lower design standards for some rural roads. Mm-hmm. And some curves are sharp, but at night, because of poor lighting, and accidents happened. And then we designed a curve warning system there. And if the approaching vehicle is too fast, then suddenly the light will flash on a curve there before that even. But then if the vehicle speed is okay, then there's nothing will turn on. So it's the same kind of logic, because there's a liability thing. If you tell them it's safe to go, and if they run into accident, mm-hmm. and then they will sue us for sure. But the same thing for this warning system. We just warn the driver it's unsafe to go. But you ask a very good question. Whether this will develop that, we don't know. We hope not. But we explain. We try to, when we really started conducting the experiment, we will tell the driver, okay, I'm still use your own judgment, but just use our as a reference. If we warn you not to go, make sure you don't go.
Okay. Older adulthood is characterized by variability, particularly in functional abilities. Do you measure functional abilities and take them into account in the studies with older drivers? If not, do you plan to account for this in future research?
Very good question. Yeah, I wish we could. given the scope of the project. But to answer your question directly, we are not doing that now. We're just, just put them in one group if their age is 65 and older. In fact, some drivers, when I talk to individually, not part of the study, but on other occasions, they're healthy and they're no problem. They can, their ability, physical, mental, and everything, they can be as comparable to other people. However, there's no way to separate out for us at this moment, so we just put them in one group. But given the fact that, of course, when people getting older, their abilities to start to become weaker. So it's a good question. That may be another project, but we'll see in the future.
Phase 2. Last question. Would this be useful for preventing looked but did not see crashes for all age groups? Any thoughts?
Look but did not see.
Yeah, this happens to me too. I can relate to this. So I look, I swear I don't see any vehicles, yet there is a vehicle there.
Wow. Yeah, that could be a reason, for some of the crashes. But the system definitely will help in this case. Okay, if it's unsafe, definitely the system will have the warning sign there. But so far, we did a field test before using. We did it in the field. We did the test. Okay, but that's not involving older driver, but our own driver. So far the feasibility, it's good, and the reliability is good. Every time we're not missing anything, and that's good. But when you get older, I mean sometimes visual acuity may not be as good, so I may not be able to see. But also you may forget. I'm not saying Alzheimer's disease or something, but it happened to me also. I have to double check. For me even, but for older driver it can be tough.
Yeah. Okay, I do not see any more questions in either the, let me look real quick, either the Q&A or the chat box.
Good.
Oh, wait, there's something in the chat. So let's see. That's a great question. So I think this one's more of a comment. Potential to prevent high volume of motorcycle involved collisions where vehicle turned in front of motorcycle.
Yeah, this is not only a technical project can maybe help, but also I think it requires some legislation, I guess, some regulation at least, because if data show that it's very dangerous to do that, maybe we should have some regulations. Yeah, it's good.